Hi. So today we are going to talk about how to compute some of the matrices, the H matrix, the F matrix, the C matrix, and the E matrix, and learn their meaning. So let's get started. Okay, first up is the F matrix. The thing to remember about the F matrix, we'll worry about the computations, but I want you to remember this key thing. The columns of F tell you how the axial line elements deform. So you should think about F as a stack of columns. That's how you should think about it, okay? We will use XYZ or XI as per convenience. So subscript 1 means x-axis, 2 means y-axis, 3 means z-axis. So depending upon when, sometimes we will use XYZ, sometimes we will use XI, okay? So remember that. Okay, so first up, how to compute H and F matrices. So let's look at it with an example. So you are given some displacement function u of x comma t in Cartesian coordinates. Let us make it specific. For example, I'm given little x, little y, little z, first vector equals, that's the little x vector, equals capital X, capital Y, capital Z, that's the starting vector, plus 0.2 x squared plus 0.1 y squared, that is first component of u, 0.3 xy, that's the second component of u, and 0.2 sine xz, that's the third component of u. Okay, so first one is x, the second one is capital X, third one is u. So you can see little x equal to capital X plus u. Okay, so we want to find h and f such that now, just like x equal to that one, we have dx equal to d capital X plus h times d capital X. So you can factor out the d capital X and write it as f times d capital X. So how do we find it? So the thing to remember is h is the gradient of u. So what the heck do I mean by the gradient of a vector? So the way to do that is that we find the gradient of each component of u and stack the gradient vector row by row. This is what we mean by gradient or Jacobian of a vector in Cartesian coordinates. So h is there. So h is gradient of u1 first row, second row is gradient of u2, third row is gradient of u3. I'm going to substitute for u from there particularly. So first row becomes gradient of 0.2 x squared plus 0.1 y squared. Second row becomes gradient of 0.3 xy. Third row becomes gradient of 0.2 sine xz. So if you do that, you will get 0.4x, 0.25, 0. First row, second row will be 0.3y, 0.3x, 0. Third row will be 0.2z cos xz, 0, 0.x, 0.2x cos xz. Okay, so if you just differentiate, this is what you'll get. Okay, so once we computed h, we find f by adding 1 to the diagonals. What I mean by that is f equal to I plus h. So you take the identity matrix and add it to the h matrix that we just described, and you'll finally get the f matrix. Okay, so what do we do with the f matrix? That's what we're going to look at next. The f matrix tells you how line elements deform at any point. What do I mean by that? I want to find the deformation of the x and y and z line elements dl1, dl2, dl3 at a particular point x, y, z equal to 1, minus 2, 3. Note that dl1, dl2, dl3 are little pieces of or increments of the vector along the x, y, and z axis and stand for the infinitesimal vectors whose components are dl1 is dx, d capital X times 1, 0, 0, which is dx times I1. dl2 is dy times 0, 1, 0, which is dy times I2. And dl3 is dz times 0, 0, 1, which is dz times I3. So dx, dy, dz are what one would call a little bit of x, a little bit of y, and a little bit of z. Think of it that way. They are the incremental scale factors, and what they do is they will take our vectors and scale them down, downsize them so that they can be tiny. How tiny is up to us, but we keep it tiny enough so that second order terms can be neglected. That's the idea. Okay. So now we are ready. We want to find the value of f at 1, minus 2, minus 3. This is step 1. So we already did that for general. We now substitute x equal to 1, y equal to minus 2, z equal to 3. And then you will get 1.4 minus 4, 0. Sorry, minus 0.4, 0. Minus 0.6, 1.3, 0. minus 0.5940, 0.820, 8020. This is what you'll get. Okay, so what does it mean? The deformed vectors are the columns of f multiplied by the corresponding scale factor. What I mean by that is dl1 will be dx times 1.4 minus 0.6 minus 0.5940. Can you see the first column of f times dx? dl2 will be the second column of f times dy. And dl3 is the third column of f times dz. You can see it's pretty easy, no? So there's nothing much to it. What this means is that the original incremental vector dl1, which is dx times i1, has now become an incremental vector which is along 1.4 minus 0.6 minus 0.5940. My vector there is not correct. The vector is shown in the column vector upstairs. The scale factor dx just scales it down to become tiny. But what it is that compared to when we started, the dx is not multiplying a unit vector. So the vector becomes longer or shorter, but it gets multiplied by dx to become tiny. Okay. This is how we find out how line elements deform. I'll show you with a specific example. And by the way, this is similar for other vectors. I'll show you with a specific visualization. So remember, we had DL1 and FDL1, DL2 and FDL2, the three columns of F. We're going to plot that, and off we go. So you can see how the columns of F change the original vectors. So the dotted lines are the original vectors. The solid lines are the new vectors. You have the red vector being the X line element, the green vector being the Y line element, and the blue vector being the Z line element. Okay, so let's play that again so that you understand how this works. So there you go. So I just took the column vectors and drew it and animated it. That's all. Okay, so you can understand how it deforms. Note that each starting line element, the dotted lines, either stretch or shrink. That's number one. And rotate towards or away from the axis during the deformation. So you can see that the red arrow got stretched a lot and it rotated away from the y-axis. Can you see? And the green arrow got stretched a lot, only slightly, but it got rotated away from the x-axis. And the z arrow shrank a bit, but it didn't rotate at all. That's the information that is there in F. Okay. The column vectors of F show you how to plot the final vectors, the solid arrows. Thank you very much.